Good afternoon, Science 20s. Our lesson today is going to be on the physical properties of hydrocarbons. More specifically, we're going to look at melting points and boiling points, as well as solubilities between alkanes, alkenes, and alkynes. Well, if we take a second and we look at this graph, and we truly study this graph of melting and boiling points of different hydrocarbons. So we'll notice that on the x-axis, we are looking at number of carbon atoms anywhere from 0 all the way up to 30 on this graph, as well as the temperatures from minus 200 all the way to 0, all the way to plus 500 degrees Celsius. Okay, we'll notice that there seems to be a trend on this graph. And that trend is whether it's a boiling point or a melting point, as the number of carbon atoms increase in a molecule, you'll notice that the melting point goes up, meaning the temperature it takes to go from solid to liquid increases. This is also true for boiling point. As the number of carbon atoms increase along the x-axis, you'll notice that the temperature it is required to break and go from a liquid to a gas to reach the boiling point also increases. So as we increase the number of carbons, we increase the boiling and the melting point of a organic compound. The question is why? So I've got some real life examples right here. So we have methane all the way to octane. So these are all straight chain alkanes going from 1 carbon, 2, 3, all the way to 8 carbons in a row. We'll notice that their boiling points go up, like we saw in the graph, minus 162 degrees Celsius, minus 89 degrees Celsius, minus 42. And we work our way up to 98 degrees and 125 degrees for an 8 carbon chain in a row. So why is it that the bigger my molecule, the more carbons that there is, the boiling point goes up? Well, that's really, really easy. And that is because when you have a bigger molecule, there is more attractive forces between those bigger molecules, right? If I have 8 carbons and they're floating around in solution with another 8 octane carbons, there is a strong attraction between these two molecules. And it's going to take more energy, because that's what a boiling point is, it's energy, more energy to break those bonds that they'll want to get farther enough away from each other that these liquids can turn into a gas. So the bigger the molecule, the heavier the molecule, the more mass the molecule, the more energy it's going to require to break those connections between molecules. Therefore, it's going to have a higher boiling point, or by retrospect, a higher melting point. So something like methane, a tiny little gas with only 1 carbon, although it's got an attractive force between it and another methane, it's way less attractive forces because it's only 1 carbon, 1 carbon. 5 carbon, 5 carbon, there's more attractive forces. It takes more energy to break those bonds. So more carbons, higher boiling and melting point. Pretty straightforward. Now, I want to also look at reactivity. And so let's look at this based on what we did on a previous day, saturated and unsaturated compounds. So I would like to look at an alkane. So we're going to look at ethane. I would like us to look at an alkene, and we're going to look at ethene. And I would like us to look at an alkyne, and we're going to look at ethyne. So we have a triple bond, we have a double bond, and we have a single bond. My question first off is going to be, who is the most saturated? And if we remember from our previous lesson, saturated are always the alkanes, the ones that have maxed out on the number of hydrogens surrounding the carbon atoms. So this is going to be ethane. And something that is unsaturated is always the substance that has a multiple bond, either double or triple. So ethene is unsaturated, and so is ethyne. There's room for the triple bond to break, right? It's like a little drawbridge, swing open. I can connect more hydrogens here. There's room for the other drawbridge to swing open. I can collect other hydrogens here. So if you have a multiple bond, you are unsaturated. Now, along with this, I also want to compare reactivity. So, ethane, ethene, ethine. Which one is the most reactive? Now, this is hard because you never got a chance to ever play with a model kit. But if we take a look at a triple bond here, when it's getting bonded together, there is a stress on these bonds. Now, if it's just a single bond, it just pushes right in. There is no stress there. For us, when we go from a single to a double, we have to pull this together. It doesn't want to be like this. It would love to spring apart. There's a stress there. There's especially a stress when we add in the third bond. And in a lot of cases, when you get your model kit new, this is actually a very hard bond to connect because there is so much stress on this. This guy just wants to spring apart. He wants to react because he does not like having that triple bond. So the molecule that is the most reactive for sure is the one with the triple bond. So that is going to be ethine. And the molecule that is the least reactive is for sure going to be ethane. So it's the difference between least reactive is the one that is saturated, most reactive is the one that is unsaturated. So reactivity always increases when you go from an alkane that is saturated to an alkene to an alkyne that is unsaturated. This is due mainly because of the instability of the double or the triple bond. In these unsaturated hydrocarbons, the bond strain on these bonds, the stretching, the bending on these bonds is so great it causes them to want to react. Remember, a bond represents a set of lone pairs. So when you put three sets of lone pairs this close together, these negative electrons this close together, they want to get away from each other. They're fighting to get away. So the more unstable triple bond, double bond it is, the more it does not want to be in that orientation, the more reactive it's going to be. So this is also true when we take a substance and we put in two double bonds or two triple bonds. More triple bonds means more instability. Well, what I would like us to do is I'm going to talk about this video and then I'm going to post this as a link in our YouTube video down below. I'm also going to post it in our Google Classroom. Please take the 3 minutes and watch this video. If we take a look at this, in this video, what we're doing is we're going to take bromine, and bromine is this orange, right, halogen. It's diatomic, there's two of them, and we're going to put this into an alkane. We're going to take a little test tube of alkane and we're going to drop in bromine. And what you're going to see happen is when this bromine goes in, because my alkane and my alkene, they're colorless. And then when I go and I drop bromine in, bromine is what on the screen here is going to make this turn kind of this yellowy browny orange color. But you'll notice that it's going to stay the yellowy, colory, browny, orange color because when this bromine goes in, there is no room on this molecule for it to accept bromine. It is saturated. So this bromine just kind of floats around in the container with ethane because there's no room for my alkene to absorb any of this bromine. So my container that has an alkane in it, it's going to look orange. Now, that is very different to when I take ethene and I drop in bromine. When I drop bromine into ethene, it's unsaturated. This little drawbridge can open and bromine can open up into two parts. And it's going to, when it joins, it now can drop on this drawbridge one bromine atom onto each side of where this double bond was. And it goes from unsaturated to saturated. You'll notice that over time, if I shake this up as they do in the video, this then will turn and my solution will go back to clear again because I don't have Br2s floating around, orange Br2s floating around anymore. The bromine has bonded into the molecule now, and that color has dissipated and disappeared. So the easiest way to tell apart a saturated and an unsaturated compound is drop in some bromine. If it was unsaturated, it's going to turn clear. Alkenes and alkynes will turn clear. Let's look at this so you can get it in your notes, and then I would love for you to watch the video I've tagged down below. Alkanes are saturated. They have no room for the bromine. Therefore, they're going to remain that browny orange color because the bromine is going to be floating around the alkane molecule. That is very different than an alkene molecule where that double bond is going to break and we're going to add a bromine on one side and a bromine on the other, and my solution will turn clear. Please take 3 minutes and watch the video down below.